In this video, we're analyzing a lens combination including two converging lenses, and the first lens has a focal length of 15 centimeters, and one of those foci happens to land right on the location of the second lens, no problem. Our second lens has a focal length of 22 centimeters, and one focuses here, one focuses all the way back here. And the grid is set up so that every two spaces represents 5 centimeters, and everything has been done to scale. Our object starts at a distance of 40 centimeters to the left of the first lens, and we're going to make an accurate ray diagram for the final image produced by this lens combination, and then we're going to verify it by analytically using the thin lens equation and the magnification equation. Now, the complication in this problem is that the image from the first refraction through the first lens lands on the wrong side of the second lens. That's called a virtual object. And it's not so bad to deal with this in the lens equation. You just treat the object distance as negative for the second refraction. But the ray diagram gets pretty tricky. So let's get started on the ray diagram. And we're going to look for the first image. And I start going through my principal rays. I take a horizontal ray off that object. That's refracted through the focus of the first lens. Then if I take a ray through the center of the first lens, it's unrefracted. And finally, if I take a ray passing through the near side focus of the first lens, that's going to be refracted parallel to the principal axis. And I get all my rays converging to a point, and that's where the first image of the arrowhead will form. Now that image has to be processed by the second lens. And certainly it can't be right to say that rays coming off of this image go backwards through the second lens. The light is just not going that direction. So we've got to figure out another way to process it. I see a ray coming in parallel to form that first image, and I know which way that gets refracted when it passes through the second lens. It gets refracted toward the focus. And the next ray is the one that's simple by coincidence. One of these rays is passing through the center of lens 2, and that's just because lens 2 is sitting at the focus of lens 1. Well, that's unrefracted, so it's got to go like this. And the final principal ray is where it gets tricky. I have to think about a ray that was converging to this first image that happened to be coming from the direction of the left focus for the second lens. In other words, it looks like this. So I dashed out the parts of that line where the light ray is not actually at. And so we have this additional ray that was headed towards forming that image on the right-hand side of the second lens. Because that's coming from the direction of the near side focus of the second lens, it'll be refracted horizontally. And now I see all three of these rays converging to a single point. And that's where my final image forms. So we can write down some approximations for what the image distance is and what the final magnification is. And then we'll check against those after we use the thin lens equation. So the image distance relative to the second lens, I call that DI2. That's about 2.5 spaces on this grid. And remember, this grid is 5 centimeters for every 2 spaces. So this gives me 6.25 centimeters. Again, that's an approximation, and we'll get the exact answer out of the thin lens equation. And then my final magnification can be approximated by looking at the height of the arrow. And the original arrow was 3 spaces high, and my final arrow is about 1.25 spaces high, and it's inverted. So we put a minus sign in there for the inversion. And the magnification is about 1.25 over 3, or negative 0.42. Now, to handle this analytically, we look at the thin lens equation and the magnification equation, and then we run through both refractions. Through the first lens, we have an object distance of 40 centimeters, and that lens had a focal length of 15 centimeters. And we plug these into the thin lens equation, and I get an image distance of 24 centimeters for that first image formed in the process. The magnification is negative DI1 over DO1, which is negative 0.6. Next, we run through the second lens. And because the image from the first lens landed on the wrong side of the second lens, that gives us an object on the wrong side of the lens. And the way you handle this analytically is to put a minus sign in front of the object distance. So the lenses were 15 centimeters apart, and the first image landed 24 centimeters to the right of the first lens, which puts it 9 centimeters on the wrong side of the second lens. So that's called a virtual object, and we just call the object distance negative 9 centimeters. Remember, the focal length of that lens is 22 centimeters. And we plug in our object distance as -9. We're going to add 1/9 to both sides. Simplify the right-hand side and then take its reciprocal to get di2. And I get 6.39 centimeters. We had approximated 6.25, so that's pretty close. Then we get the magnification at this second step. That's -di/do. -6.39 over -9. So the magnification is positive at the second refraction. This means there was no inversion of the image. And we saw that in the ray diagram. The first refraction inverts it, the second leaves it alone. But it shrinks it a little bit. And I get a magnification of 0.71 through the second lens. Now to find the total magnification, we just multiply the magnifications at each step. And I get a total magnification of -0.43. In the ray diagram, we had approximated a magnification of -0.42, so I'm happy with how close that is. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.